Hi my dear students, in this video we are going to discuss about an important application of an op-amp, which is nothing but the differentiator. We all know that the most important functions of the mathematics are differentiation, integration, multiplication, etc. So among that we are going to discuss about the differentiation. So what is meant by differentiation? Differentiation is nothing but we are finding out a derivative of a particular value. Okay, so this differentiator can perform operation of differentiation, that is the output voltage V0 is the derivative of the input voltage. Okay, output voltage V0 is equal to derivative of the input voltage, that is V0 is equal to dVi by dt. So we are going to prove that V0 is equal to dVi by dt. So this main differentiator used to find how the rate at which signal varies with the time. Okay, so this differentiator is used to find out how the rate at which a signal varies with time. So it mainly describes about the signal variation with time. So this is the simple circuit, my dear students. So we have to consider for an inverting amplifier for a differentiator. Okay, an inverting amplifier must be considered for a differential amplifier. So in inverting amplifier you have to make only one change. Okay, so in inverting amplifier the resistor R1 is being replaced with the capacitor C1. Okay, the resistor R1 is being replaced with the capacitor C1. So when you replace the R1 with C1, you will be able to get the circuit of the differentiator. And for compensation purpose you can use OR-camp, and that OR-camp value can be considered as R1. So now we can go for the particular derivation. So we need to obtain the output voltage such that V0 is equal to dVi by dt. Is it not? So what we are going to consider, we are going to assume something, and the assumptions are as follows. This is the particular node N, and node N will be considered as the virtual ground. So since there is a virtual ground, the voltage at node N will be considered as Vn, and it is equal to 0. So the voltage at the particular node N, Vn, will be equal to 0. Okay, so the current which is passing through the capacitor is calculated as IC, and IC is equal to C1 dVi minus Vn by dt. Okay, so the current which is passing through the capacitor will be termed as IC, and it is being calculated as IC is equal to C1 dVi minus Vn by dt, and this Vn is equal to 0. So you will be getting IC is equal to C1 dVi by dt. Okay, so since this particular Vn is equal to 0, you will be getting IC is equal to C1 dVi by dt. And now we are going to calculate the current IF. So the current IF which flows through the feedback network RF can be calculated as follows. So this current IF can be calculated as V0 by RF. Okay, so and you know that op-amp will be the ideal one. So this particular current IF will not move through the inside of the op-amp. So this particular RF will calculate, this particular IF is calculated as what? V0 by RF, and there will not be any current moves into the op-amp. So when you apply a nodal voltage at this particular, when you apply a nodal analysis at this particular N, you will be getting C1 dVi by dt plus V0 by RF is equal to 0. We are going to apply just a KCL here, that is the nodal equation. So what happens? C1 dVi by dt plus V0 by RF is equal to 0. That is, sum of input current will be equal to the sum of output current. So that we are going to apply. So what happens? C1 dVi by dt plus V0 by RF is equal to 0. Therefore what you will be getting? V0 by RF is equal to minus C1 dVi by dt, and V0 is equal to minus RF C1 dVi by dt. So from this equation we have derived that the output voltage is the derivative of the input voltage, including some constant called as minus RF C1. So my dear students, minus RF C1 can be considered as the constant, and this constant will have a somewhat effect on the output voltage. That is, V0 is a constant minus RF C1 times the derivative. Okay, so what we are doing here, we are just replacing a resistance R1 by using the capacitor C1, and we are finding out the value of IC, and IC has been calculated, and now we are finding out the value of IF, and IF has been calculated as V0 by RF. So now what we are going to do, we are going to apply KCL at the node N. So KCL, when you apply the KCL, what happens? Normally you will be having, you are going to add this IC as well as IF. So IC is nothing but C dVi by dt, and IF is nothing but V0 by RF. So when you add both the currents, you will be having the value equal to 0. So when you equate both the value, you will be getting the output voltage V0 is equal to minus RF C1 dVi by dt. And this particular negative sign indicates that there will be a 180-degree phase shift of output waveform to the input signal. Okay. So this particular negative signal indicates there will be a 180-degree phase shift of input voltage. Okay. So you hope you understand well about the differentiator, and this particular differentiator is an important question in this second unit. So next class we can discuss about the integrator. Thank you.